So yeah, I'm going to talk about finding planet elements in linear sections of varieties. Don't worry, I will explain each of these terms, but please do feel free to stop me at any point in time to explain things. I don't think I can get through all my slides, so just stop me whenever you want. I don't intend to finish all my slides anyway. So this is based on joint work with Nathaniel Johnston, who is faculty at Mount Allison in Canada, and Ben Lovitz, who actually just moved to Boston. He's a postdoc at Northwestern. Okay, so my main goal for this talk is to introduce a class of problems which are all about finding elements of an algebraic variety that lie on a subspace. So you're given a variety and you're given a subspace, and your goal is to find an element on it or a bunch of elements on it. Okay, so this problem has some nice connections to various other things that you may be familiar with, like tensor decomposition, some basic questions in quantum information, like certifying entanglement. And it also is related to statistical estimation problems. But the focus of this talk will be very algorithmic, so we'll mainly just focus on the algorithmic aspects of this talk. In particular, you'll see some algorithms for solving this problem. And there isn't as much of a statistical component, but I think there are actually some very basic, very nice statistical questions as well, which hopefully I'll get to towards the end. Okay, so good. But before I introduce a general problem, here's a very simple instantiation of this problem that's good to keep in mind. Okay, so here you're given a subspace, okay, and it's a subspace over matrices. So your space is this Rn cross n space. Okay, so you're looking at subspace over matrices. Okay, so this is a n square dimensional object, and you're looking at a subspace of it. And your goal is to find rank 1 matrices that lie inside the subspace. Okay, good. So here I'm not looking at symmetric matrices. Here I'm just looking at general matrices. You could look at this question over reals. You could look at this question over complexes, and they're all roughly of the same flavor qualitatively. Okay, and your goal is to just find one rank 1 matrix which is non-zero. Okay, so it should be a non-trivial rank 1 matrix that lies in the subspace. Okay, good. So, and in general, so this is a good question to keep in mind. And in general, we'll be thinking about similarly elements that, so this kind of a intersection of a subspace and a variety is called a linear section of the variety. And your goal in general is you're given some other variety, which is not the variety of rank 1 matrices, okay, but some other variety, and your goal is to again find, and you're given a subspace, and your goal is to find this linear section, or find some element in this linear section. Okay, so that's the general flavor of problem that we'll be looking at. Okay, good. But before any questions before I define the general problem? Okay, great. So just to end, before I define the general problem, let me just introduce some notation that will be useful and will ensure that we're all on the same page. So we'll be thinking about the field being either reals or complexes, and it doesn't matter. You can think about your favorite field. Okay, a variety is just a set, a subset of points which are common zeros of a given set of polynomials. Okay, so here the polynomials are f1, f2, f3 up to fp, and the variety is just given by the set of common zeros of these. Okay, and in that case, we'll say that these polynomials f1, f2 up to fp cut out the variety. Okay, good. And specifically, we'll be looking at special varieties called conic varieties. If you are familiar with more familiar with these things, these are the same as projective varieties. Okay, but these are just varieties where any scalar multiple of a point is also on the variety. Okay, so if you take a rank 1 matrix and scale it, it still remains rank 1. Okay, so these are called conic varieties, and this will be the focus of our talk. Conic varieties will be the ones that we'll be looking at. And one nice thing about conic varieties is that you can always choose the polynomial. You can always choose a set of polynomials that cut out the variety to be of the same degree. And furthermore, you can choose these polynomials to be homogeneous. Okay, so in general, we'll be dealing with conic varieties, and we will assume that we are given such a homogeneous set of polynomials that cut out the variety. Okay, good. So that's really all you need to know about varieties at this point. Okay. And so let's look at rank 1 matrices, and we'll see why this fits into this picture. So rank 1 matrix is just the order product of two vectors. Okay, so yeah, I mean things of the form U1 V1 transpose. We will use that tensor product notation to just mean order product. Okay, and yeah, so this is actually a conic variety that is cut out by degree 2 polynomials, a set of degree 2 polynomials. Okay. Any guesses as to what these polynomials are? Exactly. These are the 2 cross 2 determinants. Okay. So if you think of a matrix, you can look at all the 2 cross 2 determinants that are formed by looking at 2 cross 2 submatrices, and all of them have to be 0 if it's actually rank 1. Okay. So this is an if and only if condition, and these are a set of linearly independent homogeneous polynomials of degree 2 that cut out this variety. In general, if you're thinking about the variety of rank R matrices, you should look at R plus 1 by R plus 1 submatrices. And if it's an if and only if condition again, that if and only if all these determinants are 0 is the matrix of rank less than or equal to R. Okay, good. So this is exactly why it fits in the framework, and in fact, the degree here is just 2. Okay, good. And what's our problem? So we are given this conic variety, okay, and we are given a linear subspace, and your goal is to so we are given this variety in terms of all these polynomials that cut out the variety. There could actually be multiple sets of polynomials that cut out this variety. We are assuming that we are given one such set of polynomials that cut out x, and you're given a basis for u, and your goal is to either find a non-trivial element in this linear section or certify that it's empty. Okay, if the intersection is trivial. Actually, that shouldn't be empty. That should just be trivial because 0 is always in the intersection. Okay, and our goal is to design algorithms that run in time that is polynomial in the dimension n. Okay, so for rank 1 matrices, capital N is n square, small n square, and the dependence on d could be exponential. Okay, and that's a very natural reason for this, and that's because when you think of these set of degree d polynomials that cut out the variety, you can always just specify a bunch of linearly independent degree d polynomials that cut out the variety. There are at most so many degree d polynomials. Okay, so this is really like polynomial in the input description. Okay, good, great. Any questions? Okay, so this is I think it's a very natural algorithmic problem. It has connections to quantum information, and we'll see that it has nice connections to low rank decompositions. And it also has the flavor. This is more of a, this is reminiscent of problems like matrix sensing and tensor sensing, because they do correspond to things like linear measurements of your object of interest. Okay, good. So I'll actually go into more of these motivating examples later, but let me talk a little bit about the algorithmic question. So this question is NP hard in the worst case. Okay. And it's NP hard even for the variety of rank 1 matrices. Okay, and that's just because you can embed problems like solving a system of quadratic equations. Okay, and that's NP hard. And the best known algorithm for this solves a slightly different problem, which is like a promise version of this problem. Okay, where you're either promised that you're given an element in the variety, or every element in the variety is epsilon far from the subspace, and it solves it in quasi polynomial time. Okay, this is a very nice work. And yeah, so that's the best known algorithm. But this is all in the worst case. Okay, so I guess we don't expect to. We're not looking to get better algorithms of this flavor. We are looking for polynomial time algorithms. So you need to make some assumptions. Okay, so and what we'll be focusing on are typical inputs or generic inputs. Okay, so the way you should think about it is you're given, you're going to look for an algorithm that works almost surely. Okay, over the instance space. Okay, and there's a precise way of capturing it in algebraic geometry, and that's just by saying that your algorithm works over a set that's Zariski open dense. Okay, that just means these sets have measure 1. Okay, so that would just mean that it works on essentially almost surely over all inputs. Okay, but here's a nice this is a bit of a mouthful. Okay, but maybe here are a couple of nice ways of thinking about generic guarantees. one way of thinking about generic subspaces is you can just think of a random subspace, a random r-dimensional subspace. Okay, that, I mean, if you have generic guarantees, it would mean that it works over when your subspace is chosen randomly. But here's a more interesting way of thinking about generic subspaces. You can think about a smooth analysis version of it. So, you think of an arbitrary subspace, so think of a basis for an arbitrary r-dimensional subspace, and then you just perturb each of these basis vectors a little bit randomly. Okay, so this perturbation is given, you can think of a Gaussian to do this perturbation, you can think of other distributions as well, but just think of this perturbation as being really tiny, tending to 0. Okay, yes?
So I'm confused. I thought you would want to plant something in the subspace.
Good, we'll get to that.
The answer is usually
That's exactly right. So yeah, you're just getting ahead of the next slide, and I'll talk about the exact planted version of this question. Okay, but you're right. If you don't do anything else, the intersection is going to be trivial if the dimension is small enough.
But also, if you plant, I mean, it's hard to interpret it in terms of like the open dense set.
Yeah, so you should think about the topology induced by the variety. Mm-hmm. Okay, yeah, and then you look at what are open dense sets and so on.
Okay.
Yeah. Good. So the way to think about a generic subspace is you just take an arbitrary subspace and just perturb the basis elements just a little bit and look at that subspace. Okay, that's a smooth analysis version. And if you just think of this perturbation, the smooth analysis random perturbation is going to 0, that would give you a generic subspace. Okay, good. So these are the kind of instances we'll be thinking about, but what's the exact planted question? Okay, so here's a fact that will motivate our model, and that's exactly what Ankur alluded to. Okay, so if you take a generic r-dimensional subspace, okay, its intersection with your given variety is going to be trivial as long as the dimension is at most some number r0, which is given by the dimension of this variety. It's called the Krull dimension of the variety. The dimension of the variety is there are many ways of defining the dimension of a variety. But it's quite complicated. We won't need it for this talk. Okay, but there is a notion of dimension of varieties. Okay, and it's a very basic fact in algebraic geometry that if you take a generic r-dimensional subspace, then its intersection, if r is less than r0, where r0 is basically the codimension of the variety, then its intersection will be trivial. Okay, so for example, if you think of the space of rank 1 matrices, then r0 here is just n minus 1 squared, whereas the dimension that it lies in is n squared. Okay, so it's almost the whole thing. The difference is just 2n minus 1. Okay, good. So what's a natural way to think about a planted version of this question? Well, you just think of a generic r-dimensional subspace where S of them are chosen generically from inside the variety. Okay, so think of a subspace that is spanned by S elements that are chosen generically from the variety, and the remaining r minuses chosen from the whole space. Okay, so this is a very natural way of thinking about generic planted instance of the problem. And here there are exactly S planted elements of the variety inside the subspace. Okay, and because this R is less than this codimension of the variety, you know that there are no other planted elements in the variety. Sorry, there are no other elements of the variety in the subspace. Okay? Good. Any questions about this model? So this is the planted setting that we'll be thinking about. Okay, and our goal is to design a polynomial time algorithm that computes this intersection almost surely. Okay, and here, you can actually just compute the whole intersection because there are only S elements of the variety, which lie on the subspace up to scaling. So we can just hope to, enumerate all of that. Okay, up to scaling.
Can you just make the one-dimensional matrix case? Can you just instantiate it with this?
One-dimensional matrix case. So n is 1. Sorry, I didn't quite understand.
I guess.
Rank 1 matrices. Yeah. So that's, you want me to repeat the, good. So if you think of all n cross n matrices, that's a space of dimension n squared. Okay. Now, it turns out that the dimension of the variety of rank 1 matrices is actually 2n minus 1. And it's actually easy to see because of just parameter counting. right? You have vector u and a vector v that you have to guess. That's 2n parameters, but you can always scale. So that's one less parameter. So that's like 2n minus 1. Okay, so that's the dimension of the variety of rank 1 matrices. And so this is really the difference is n minus 1 square. So that's the codimension. Pardon?
I guess I'm not understanding this like red box, the planted instance.
Good. So what's the planted instance? So think of R as being, let's say, n squared over 2. Okay, so that's the subspace dimension that I'm going to think about, or n squared over 4. Okay, I'm going to have maybe one rank 1 matrix inside the subspace, or maybe a few. Okay, and the rest are just chosen generically from the ambient space. Okay, so but you can a priori pick a dimension you want, like n squared over 4, that's less than R naught, and then you'll be guaranteed that the only rank ones that are in the subspace are exactly these ones that you picked.
Like you're saying that you're choosing a couple of rank 1 matrices to define your subspace. And
Yeah.
then you're completing it.
Yeah, exactly. So you pick a bunch of generic rank 1 matrices, and then a few other elements, so that it spans the subspace of your required dimension. Okay, good. Any questions? Great. No, these are all great questions. Thank you. So I guess the main takeaway is that even though this problem is NP hard in the worst case, you can actually design polynomial time algorithm if the subspace is generic and the dimension of the subspace is not too large. And here we'll be able to go up to constant times the maximum possible dimension. Okay, so that's the main result, and this holds for rank 1 matrices, but it also holds for general varieties as well. And there, yeah, it depends on certain parameters of the variety. Okay, so that's the main takeaway. But I'll get to the result in a bit. Okay, good.
What was known, maybe you said this,
Yeah.
what was known for like the specialization of this to rank 1? Like would you say
So
planted rank 1 matrix in a random subspace?
yeah, so the only work I know of is this paper by Barak, Kotari, and Steurer, which gives 2 to the root n over epsilon.
That's like very close to doing worst case, right? Like what
That
if
is the
I
worst
make
case
a
result.
planted- If I do, oh, I see. But you allow generic, so this is like a less strong assumption than.
Yeah,
This is
it's not
also
random.
Yeah.
Yeah.
It's also related, but it doesn't fit into the same framework as like the sparse vector in a random subspace.
Correct.
But there it's not I mean, it's a different kind of geometric constraint.
Yeah, that's right. So yeah, if you want to think of it as a variety, it's too high degree.
Yeah,
So
Yeah,
the sparse
yeah.
vector in a subspace variety.
Pardon?
Sparse
Yeah.
vector. Sorry, go ahead.
Yeah, sparse vector in a subspace, it's not useful to think about it as a variety because then you have to go to degree s if it's s sparse or s plus 1. But yeah, small rank matrices are a nice variety to think about. There are a bunch of others that maybe we'll see later. Yeah. But okay, so I guess your question is what about the average case results that are known for these problems? And I don't know how well these are studied for like, planting a random rank 1 matrix in a subspace. Yeah, I don't know how, yeah, I mean, there might be nice results known, but I don't quite know what's known. Yeah.
I think it is more also the fully dense case if you plug like a Boolean vector in a subspace.
Boolean rank 1 matrix, you mean? Like,
Plus or minus one vector.
ah.
And it goes past this, right? I think it's fixed.
Oh, so good. So that's a great question. And this is exactly why you need it to be a conic variety. Okay, so you can't, yeah. So because it's conic, you can't capture Boolean constraints, you can't capture, yeah, so otherwise you can capture things by saying x square equal to 1, xi square is equal to 1, and summation xi is equal to k. But we can't, yeah. Yeah, so that doesn't work, and it's good that it doesn't work. Because, yeah, there's probably some, hardness that you can show. Yeah, thanks, it's a great question. Okay, good. So just a couple of the motivating things, just to get a sense of why these results may be interesting. So for example, this application to quantum entanglement. So an entangled, I mean, this is just one slide of quantum information. So in quantum information, a product state is in a bipartite system. A product state is just one, which is just a tensor product of 2 vectors. Okay, so product states are those that are separable and they are not entangled. Okay, so these set of states, which are all written as product vectors, it's exactly the same as rank 1 matrices. Okay, so often, I mean, so one important problem in quantum information is given a subspace, you want to determine if the subspace is entangled. That means you want to certify that there is actually no product vector that lies in the subspace. Okay, in other words, you just want to show that, I mean, the linear, I mean, U intersection with rank 1 variety is trivial. Okay, so this is exactly the same question specialized to rank 1 matrices. Okay, and this has applications to entanglement witnesses. There's this thing called range criterion for mixed states, error correction, and so on. Okay, and there's a very closely related problem called quantum separability, which has a lot of other connections. And there are also various other notions of entanglement that have been studied, particularly for multipartite systems, like genuine entanglement, complete entanglement, and so on. And they're just captured by different choices of the variety. Instead of looking at rank 1 matrices, you can look at some other variety, and many of these things just apply.
Sorry, can I take you back to Ilias's question? I'm still
Yeah.
slightly confused. I
Sure.
hadn't thought about it in that context.
Yeah.
So definitely if you plant like a plus minus one, vector and a random subspace, things seem to be hard. So here you couldn't make it conic by looking at the
Homogenization.
variety. Yeah, that's right.
Yeah, I thought about it, but there were some issues. So
Okay.
okay, maybe there are certain other things that come about. Like we need a little more about the variety. I've only been talking about rank 1 matrices,
Okay.
and maybe some of these fail.
Okay.
But also, okay, yeah. Maybe we'll revisit this question at the end. There was something that
somehow like some
Yeah.
stuff over there
Yeah,
says
yeah.
something should be hard, and
yeah.
something over here is easy.
Yeah,
so-
no, yeah,
Okay.
yeah. I've lost sleep over it a couple of times. Yeah.
You know this polynomial coping small, right? And you get something like n to the degree. I think the hardness is like n to some constant. So I'm not sure. I'm not sure it will contradict you.
Oh, you're talking about Boolean, finding a Boolean vector, but that's probably sample complexity that you're thinking about. I mean, like, is it a question of number of samples that you need, and there's some hardness depending on? Yeah. So here there's no sample complexity issues. It's just an algorithmic question, and then yeah, but there is still the question of maybe you can try to embed things like clique and so on, but yeah, I don't think you can. Okay. Good. So the other yeah.
So, rank as matrix file sensing would fit into this framework, exactly.
Yeah.
Right? Like without
Yeah, that's a good question. It's just that the rank is, you should think of the rank as being a constant then.
So S is not the right rank to think about?
Well, rank, so our dependencies will have an exponential dependence on the degree, and the degree is basically the rank of the matrix that you look at. So,
No, but in your formulation, like if you
Yeah.
plant S rank 1 matrices and take a
Oh.
linear subspace, it's essentially finding a rank S matrix.
no, it's not. It's very different actually. Yeah. You're thinking of one rank. I mean,
So
planting
S
one
rank
rank
one-
S matrix is very different from.
So here,
Thinking
like,
of-
he wants to find a rank. Yeah. I mean, this gets easier when S is growing, right? When the number
Yeah.
of planted
Yeah.
rings.
Yeah.
Um,
That's right. Yeah. Okay, so maybe another application to think of is tensor decompositions. So tensors are just multi-dimensional generalizations of arrays and matrices. And a decomposition, the standard notion of tensor decomposition called CP decomposition is it tries to express your given tensor as a sum of rank 1 tensors. These are simpler objects, rank 1 tensors, and you just want to write it down as a sum of rank 1 tensors. Okay? And this is a really beautiful question, and there are some amazing uniqueness results that are known for tensor decompositions. There's an amazing mathematical fact. Tensor decompositions of order 3 and above, for tensors of order 3 and above, are generically unique. Okay, under some very reasonable assumptions or generic instances, they are actually unique. And this is true only for tensors of order 3 and above. It's not true for matrices. Okay? And this problem is NP hard in the worst case, but you can also get polynomial time algorithms under some reasonable assumptions. And that has been extremely useful for many applications in machine learning where you can design polynomial time algorithms for parameter estimation of various latent variable models under some reasonable assumptions. Yeah. It need not be necessary. Yeah, this is just an example that I picked, but it doesn't need to be symmetric. Yeah. Good. So it turns out that one of the best known algorithms, again, a very popular algorithm for tensor decompositions is this algorithm called FUBI, which is by Delatour, Castellan, and Cardoso. And the way this algorithm works is it basically computes, by flattening out this tensor, you can actually find the span of these AI tensor twice, where AIs are the factors of your tensor. Okay? And it turns out that what this algorithm basically does is it just finds the linear section that is given by you. So it just finds all the rank 1 matrices that lie inside the subspace. Okay? It's just an algorithm to enumerate all the rank 1 matrices that lie inside the subspace. And this is a subspace that you can find from the given tensor, okay, by just doing SVD on a flattened matrix. Okay? And that actually gives you a polynomial time algorithm, and they have this claim that it works for generic instances up to a certain rank, and this is the best known result for generic tensors of order 4. Okay?
So for FUBI, I mean, I'm not aware of any like stability analysis of it.
No, there is.
Okay.
You can, under a smooth analysis setting, you can actually get robust guarantees as well. I mean, there's also explicit conditions. Actually, there's a paper by Sleel, Shi, and you, Sam, is it? Yeah.
Yeah, but I mean, it's not for FUBI. It's
Yeah, it's a modification of FUBI.
My paper is just like trying to do a little faster, but I think the
Yeah.
guarantees, if you just want polynomial time, come from the paper by David and Tengu and Jonathan.
Yeah, that's a sum of squares based algorithm, but we actually gave a robust analysis of FUBI.
FUBI itself.
Yeah.
FUBI
Yeah.
itself, okay.
Yeah, but with worse constants in the rank. Yeah. Okay, but the main idea again is just finding this linear section of a variety, and here you actually want to enumerate all the elements. Okay, good. So so the main result. So so let's just look at the result for rank 1 matrices. So here we can show that for rank going up to 1/4 of the maximum possible dimension, you can actually solve this in polynomial time for generic subspaces. Okay, so for the generic instance where you plant at most S elements of S rank 1 matrices in your subspace and complete the subspace, and it's of dimension at most 1/4 times n minus 1 square, you can actually find all the elements in polynomial time. Okay, and so this also, this is up to 1/4 of the maximum possible, and this also gives you new guarantees for certifying entanglement. Again, it's more of a generic result. And for tensor decompositions. Okay. It gives you new guarantees for tensor decompositions in some non-symmetric settings. So here's actually any question?
How did the result depend on S? Where does S feature?
So this is only for rank 1 matrices.
No, but there is an S, right? You plant S.
Oh yes. There is no dependence on S.
There is no dependence.
Yeah. So basically, if you plant up to R elements, you find all R elements. If you plant only 2, you find 2. Yeah.
So even one.
They're just going to stick out, and you'll just find all of them. Okay. Yeah. Thanks. Okay. Good. So this also extends to general varieties, and here we need to make some assumptions. Okay. So maybe go over this a little more slowly. But so here we are given a variety which is cut out by these many linearly independent homogeneous degree D polynomials. Okay, so the way to think about it is you have this many polynomials in total. That's the dimension of the set of all homogeneous degree D polynomials. And if your variety is cut out by delta times that many of them, okay, for rank 1 matrices, for example, it was 1/4 times the total number of degree D, the dimension of degree 2 polynomials, right? So if it's delta times that, then you can go up to rank, which is delta divided by some dependence on the degree times the maximum possible dimension. Okay? So there are a couple of assumptions. We assume that the variety is irreducible. That's not really an assumption that's needed. It just makes the guarantee simpler to state. But there is an assumption that the variety has to be non-degenerate. It just means that it's really a variety that's cut out by degree D polynomials. You shouldn't have any degree D minus 1 polynomial or lesser that becomes 0 on it. Okay? And many varieties of interest actually fall into the setting, and many of the things that we'll be interested in satisfy these conditions with delta being a constant, so we can go up to constant times the maximum possible dimension. Okay, again, this is a generic result. And this parameter P is actually a very natural quantity that comes up in algebraic geometry. It's related to what is known as the Hilbert function of the variety at D. Okay. Good. And good. Regarding irreducibility, you can just apply the same theorem. So an irreducible variety is just one that cannot be written as a union of other varieties. Okay. And you don't need the irreducibility assumption. You can just apply the same theorem to every component. Okay. Non-degeneracy is something that we need, and it's clear that something is needed, but I don't know if that's the right condition. Okay. Yeah. So this is the result for general varieties. Any questions?
Can you tell us about the algorithm?
Yeah. Okay, I'm going there. Yeah, but I guess yeah, this also works for a bunch of other varieties like Schmidt rank R varieties. That's yeah. Okay. Slice rank, matrix product states, and so on. Okay, and maybe one more result before I just go into the algorithm. So it also allows you to, tensor decompositions always seem magical to me because you get this uniqueness result, which is very unique, very special for tensors, right? But it turns out that it is actually, you actually get these uniqueness results and polynomial time guarantees for a class of low-rank decomposition problems. Okay, so here's a class that you can think about. So here your tensor, you can think of it as a matrix, it's just given by a low-rank decomposition where these VIs that are, in this decomposition actually come from your variety. And your WIs can be, from the whole space. Okay? Or it could also come from the variety, that's fine too. Okay? So it just has a low-rank factorization in terms of the elements of your variety. Okay? And in this case, you can actually get uniqueness results and polynomial time algorithms under very similar conditions. Okay, so as long as the rank of your tensor, okay, in terms of its decomposition, is at most this delta divided by d factorial. So think of this as a constant times the maximum possible dimension. Then you actually have, it's a mathematical statement that there's a unique decomposition, and you can actually recover this decomposition polynomial time. So things like Fooby and other tensor decomposition algorithms that are known, they actually fall into this one general framework. Okay. And this is kind of nice because maybe this opens up maybe a powerful family of algorithms that may be useful in other settings. Okay, good. And for people who think about tensor decompositions, there's always this nagging issue of non-uniqueness that comes from matrix decompositions. So matrix decompositions are not unique. Okay, there's this rotation problem. And that doesn't happen here precisely because of this non-degeneracy of the variety. And you need the non-degeneracy to ensure that you have uniqueness. Okay, so if you, yeah, I can go into that more later. Okay, so any questions before I move into the algorithm? And okay, good. So before so just a reminder, we are given your variety in terms of these polynomials that cut out the variety, and you're given a basis for the subspace. Okay, just one bit of notation. We'll think of, the symmetric lifting of given a vector space V, SD of V is going to represent all symmetric tensors on that subspace. It's just a symmetric lifting of this subspace. Okay, it's just all symmetric tensors that can be defined over the subspace. Okay, good. So let's think of the simpler case where there is actually no planted element in the variety. And your goal is to just certify that the intersection is trivial. Okay, this is certainly true mathematically, but your goal here is to give an algorithm that certifies it. Okay, so a couple of simple facts. Okay, so and this is actually the description is mostly going to be linear algebraic. These all have natural analogs, and they all make sense when seen from an algebraic geometry language as well. But this is all we are going to use about these polynomials. Okay, so every degree D homogeneous polynomial, you can think of it as a linear function, but over this lifted space. Okay, so f of v, where f is a polynomial acting on v, you can just think of it as a suitable linear function acting on v tensor D. Okay, this is just a very natural thing. And then, so here is just an extension of this. So for any variety, any such variety that you have been looking at, you can actually construct a linear map. That is a linear function. Okay, so a linear map where every element of your variety is characterized by this. So every element of your variety satisfies that the dth lifting of it is in the kernel of this linear map. Okay, that's just because we are just lifting everything into this default tensor product, and there it's just linear in that space. Okay, so these are the two facts that we will use for this informal description. Okay, so let's look at. Yeah.
So here, I mean,
Yeah.
so this is an interesting way to think about it. So I mean, like Fooby is an instantiation of this for like a particular linear map.
Exactly.
I guess,
The
right?
rank 1 detector.
So
Yeah.
here, I mean, it's kind of seems a bit surprising that you can do this in this
Yeah,
general.
you can just do this for any variety. Yeah, exactly. So in some sense, Fooby was a starting point. It's a very fixed, specific linear map that corresponds to the rank 1 detector, but you can do this for any variety. Okay, so actually a certificate is just inspired by this very well-known thing called the Hilbert Nullstellensatz. Okay, and how do you want to? So suppose you have this non-trivial point which is in the subspace but also in the variety. Okay, so what does it mean? Well, you know that so it's in the subspace, so you can write it as a linear combination of your basis elements. But furthermore, we know that because it's in the variety, you know that the default tensor product is in the kernel of the linear map. Okay? So just expand it out. Okay? And if you just expand it out, you can easily show that, if there is an element which is in the variety and in your linear subspace, then it means that all these vectors, these are actually, vectors in a higher dimensional space, these all become linearly dependent. Because there are valid coefficients alpha, okay, which allow you to, which will tell you how to combine all these different vectors, and which will have to be 0, because the linear map is 0 on this default tensor product. Okay, so any point is a witness to the fact that these vectors are linearly dependent. Okay, any non-trivial point which is in the intersection is a witness to the fact that these are linearly dependent. So now here's a very natural certificate for showing that, certifying that it is that intersection is trivial. You just try to see and check if all these different vectors are linearly independent. Okay? If they are linearly independent, then it means that the intersection has to be trivial. Okay? If not, you give up. Okay? Good. So this is actually nothing new. This is the Hilbert Nullstellensatz certificate. Okay, this is for projective varieties. But the main contribution of our work is to show that this Hilbert Nullstellensatz certificate, even at the first level, actually does pretty well. Okay, it works for subspaces going up to a fairly large dimension. Okay, so that's the main technical thing. You want to show that all these vectors are linearly independent for a generic choice of u1 to ur. Okay. And this is an equivalent claim. So just think of the kernel of this linear map. Okay, that's the subspace. And you want to argue that the kernel of this linear map intersects trivially with the symmetric default lifting of the subspace U. Okay, that's really what you have to show. Okay. So you could hope that this is just a statement that's just you can just try to do some dimension matching and hope that if you actually pick your dimension of your subspace large enough so that the dimension of W plus the dimension of this symmetric default lifting of U, if it is less than the total dimension, then you could hope that this is true. Okay. In fact, this is something that was claimed by Delatour in one of his papers. In fact, the proof of the Fooby algorithm relies on it. It turns out that it's false. Okay, it's not true that if you just line up the dimensions, that you should hope for it to be true generically. Okay, it's not even true for very small dimensions. So this is not quite true. But you can actually show that something like this is true with a slightly small, with a small loss in the dimension of the subspace. Okay, so we're going to show this, and another way to show this in algebraic geometry is if you show one set of instantiation of these vectors u1 to ur where they are linearly independent, then it's true for a generic choice. Okay, that's something that's really nice, except that we don't know an explicit choice of u1 to ur. It turns out that the thing that actually managed to work was a probabilistic approach. Okay, so where we were we showed that there exists an instantiation because you can do this randomly, and a random choice works. Okay, and it turned out that it was useful to do this random choice because then you could try to decouple certain random bits that come up in the choice of these vectors. Okay, so I'm not going to go into the proof of this, but it turns out that some of these things that were known in the TCS community actually ends up being useful here. Good. And then the algorithm for planted instances, this is just for certifying that the intersection is trivial. For finding these elements that are in the intersection, here you can again recall that, so we showed that, so if V is in the variety and V is in the subspace, then you can just write down this equation and expand it out in terms of these alphas. Okay? Now you can just write down a system of linear equations where you replace all these product variables involving these alphas by a separate new variable. Okay? And just write down a linear system, and you can try to solve this linear system. Okay? Our Hilbert-Nullstellensatz certificate showed that this linear system itself only has a trivial solution. But here, of course, we expect solutions because we have these planted vectors. Now you could hope that all valid solutions are the rank 1 solutions that you care about. Okay, but of course this is not true because it's a linear system, so any linear combination of solutions is also a solution. Okay? But it turns out that what you can do is you can actually look at all these different solutions, and they will all have a simultaneous decomposition in terms of your planted rank 1s, okay, or your planted elements of your variety. And that's really the algorithm that we use. And you again need some kind of a similar condition that I talked about earlier to prove correctness, and this is something that we managed to do. Okay, so that's the main crux of the argument. Okay, so okay, good. So that's the result again, and maybe let me just conclude very quickly. So so I guess in this talk we looked at this fairly broad class of problems involving finding linear sections of varieties, finding an element or finding all the elements in this intersection of a variety and a subspace. And we looked at a planted instance of this problem. And we can design polynomial time algorithms if the instance is generic and the dimension is not too large. Okay? And there are a bunch of nice questions that I think would be good to resolve. So even in the specific case of the variety of rank 1 matrices, we can go up to 1/4 of the maximum dimension. And it's not clear to me whether it should be hard, going all the way up to the codimension of the variety, or whether there's some hardness that creeps in somewhere. Okay? And in fact, even beyond this codimension of the variety, you should start seeing many elements of the variety in the subspace. And again, you could ask the question of, can you find one of them? Okay? These are all versions of the question, which is again, this is not worst case instances, these are generic instances, so you could hope for algorithms, but I don't know if it's easy or hard. Okay. And another question that is actually very interesting and actually very useful from application standpoint is, maybe you're not given the subspace exactly, but you're given a small perturbation of the subspace. And that's usually what happens when you look at applications that come from machine learning. And then your goal is to not find all of the elements exactly, but you only want to find it up to some error. Okay? And then here, genericity as such will not be enough. You'd need something like smooth analysis to hope to get some polynomial time guarantees. Because smooth analysis is the right quantitative quantitative analog of genericity arguments. Okay? So that's something else that would be interesting. Yeah, and in general, I think there are a lot of nice questions at this interface of high-dimensional statistics, algebraic geometry, and so on. And I think, it'll be nice to explore these questions further. Okay, thank you.